Now, let's turn to another application, which is system reliability. Now, this actually is new. This is the first time I've presented this, and it was stimulated by a question. I think it was David Jackson's question about Weibull distributions and basically the importance of failures and the timing of failures of components in systems when you don't have very much data and you can reasonably assume that the shape is reasonably modeled by a Weibull distribution, which many, many people in systems reliability do, and appropriately so. Well, it caused me to start thinking about this a little bit, and I checked with Sam and Phil, and he said, well, yeah, they both said, well, why don't you go ahead and create an example along these lines? So this is what I've done here. Now, first of all, the reliability of systems has been extensively researched, and this is just from Google Scholar. You just look up the reliability of redundant systems, and particularly, you see, reliability of independent systems. We know, for example, that the minimum of independent Weibulls is in fact a Weibull distribution. So that is, those kinds of things are known, but when you've got redundant systems, that is, you've got two engines on an aircraft rather than one, or two of any part, which if one fails, the other kicks in, so the system doesn't fail, those are called redundant systems, and there's a lot of redundant systems, and this is real life, that depend on what are called common failure modes, right? If something in front of those common systems fail, common components fail, then they both fail, right? And that means that their failures are correlated, and that's something that is not, has not been, let's say, easily or conveniently modeled. But yet, nevertheless, there are a lot of articles on this topic. People have thought about it, and I'm not in any way proposing to displace all this literature. What I'm really just trying to do is illustrate another way in which metalogs can be used to simplify a problem that otherwise might not have a simple and easily interpretable mode. And a great example is single engine versus dual engine aircraft with potential common failure modes, right? I don't know what happens. The electrical system fails or something, and the engines both fail. I don't know what it is that would cause them both to fail, or the fuel lines or something. I don't know, but or maybe even the same manufacturer versus different manufacturers. Who knows? So anyway, that's the example that I worked to put together here. And the question is, can metalogs provide a new way to simplify and facilitate such analyses? So first observation, and this is just along the lines of the sum of log normals, we observed previously, and this came from a previous session, but we observed previously that if you parameterize a log metalog, and I'm once again using the 9-term log metalog, with parameters from the Weibull distribution. So here is a Weibull distribution with a shape parameter of 1.5, and these are the y coordinates on these are the probability coordinates on the CDF that correspond to that. These are the exact Weibull parameters that you would get when you just ask your statistics calculator to calculate them. That's what they are. If you parameterize a log metalog distribution with those exact 9 parameters, you get something that goes through all 9 parameters exactly. And if you do what we did before, you say, well, how close are the density functions to the exact Weibulls? Well, you can see the exact Weibulls here are in blue, and the dashed yellow is the 9-term log metalog parameterized by those Weibull parameters. And once again, you see you get something that is so exact, you really can't tell the difference in a practical sense. So that's for a single. Now, this is not saying anything terribly magic, because all it's really saying is that any given Weibull distribution does have a log metalog representation, which is effectively the same distribution. That's all I've said so far. However, we might be asking a question such as, how does adding a redundant component, a second engine, for example, or a second braking system, or a second whatever it may be, fuel line, parallel fuel line, whatever it may be, how does adding a redundant component improve system reliability? And we might be interested in that both as a function of a Weibull shape parameter k. Let's say each individual component is Weibull distributed in terms of its failure time. And that shape parameter, Weibull shape parameter, determines basically the nature of how the failure changes with the age of the system. So for these Weibull shape parameters greater than 1, basically the system is like the human body in a sense. The older it gets, it's more likely to fail, okay? Or at least many people would think that. If you're down here less than 1, the Weibull shape parameter effectively means it's like infant mortality. The younger systems tend to fail more frequently than the older systems after they're burnt in. This Weibull shape parameter of 1 causes the Weibull to reduce to an exponential distribution. That says that the rate of failure doesn't change depending on how old the system is. But you might be interested in knowing, how does adding a redundant component improve system reliability, both as a function of the Weibull shape parameter and common failure modes, which in this case I'm going to model as a correlation coefficient. Now, there are more sophisticated ways of modeling that, but let's just say that if the two components are independent, that's a correlation coefficient of 0. They could be dependent with a correlation of coefficient of 0.5 or 0.9, or they could be strongly dependent or even anti-correlated, I guess, in principle. I think it's unlikely to happen in real life, or at least I'm not aware of it. But the question is, so that basically adding a redundant component is the maximum of two identically distributed but potentially correlated Weibull distributions, which has no known closed form. But it's a well-defined distribution as a function of the correlation coefficient rho and k. And for any selected reference probability vector, which is this one, we can, again, simulate it a large number of times. And in this case, I did 500,000 simulations, which is about the most my particular computer can do in an hour. You may want to do more. But we end up with a table of quantile parameters. And here they are. If they are for 0, they are independent. And the shape parameter of 1.5, you get this, right? And this is for a lambda, a scale parameter of 1. But again, this can always be rescaled according to different lambdas, so that can be done after the fact. But here's your shape parameter. So one question is, well, what, an important factor here, important fact is this simulation only needs to be done once and stored. It's not like you have to do it every time. And this also has the same property that any linear interpolation in between is feasible if all the cells in this table are feasible, which it turns out they are. So let's take a look at these. Let's see what they look like. So here I'm just going to do an illustration for Weibull shape parameter k equals 1.5. This just has a little bit of this effect that as a system gets older, it's more likely to fail. And I'm going to do it for different correlation coefficients, 0.99 to minus 0.99. And the first one plotted there is the 0.99. So I've got the maximum of two Weibulls that are 100% correlated, or 99.9% correlated, let's call it that. And what that gives you, in effect, is the Weibull distribution itself. Because if two distributions are 100% correlated, then basically if you have a high outcome of one, you have that same high outcome of the other. Excuse me. So you end up back with the original distribution. Now, what happens if instead of being 100% correlated, they're 90% correlated? Well, that means you could have a higher maximum in one without having a higher value of the other. And so you would expect that would cause the curve to shift to the right. And in fact, it does. There it is for a correlation coefficient of 0.9. Here it is for a correlation coefficient of 0.5. Here it is if the two components are independent, and we're looking for the maximum failure time of the two. Here it is if they're anti-correlated, that is, if one fails, the other is less likely to fail. Minus 0.9, and in the extreme case of complete anti-correlation, you end up with this odd shape here. But you can see why it happens, because basically if one is low, then the other is guaranteed to be high, so you can't get something that's too far away from the middle of the distribution, which is what this curve is showing. The negative correlations are ones I've shown as dotted lines here because they're, as I say, I think they're more likely to occur based on wishful thinking than they are to occur, actually in practice. And you may correct me on that, and that's fine. We can have that as part of the discussion. But in any case, that's what they look like. And I don't know that these have ever been seen before. I've never seen sums of correlated Weibull or maxima of correlated Weibulls displayed as probability density functions. And that, maybe somebody's done it. I'm not aware of it. But it would be hard to do without the metalogs, because how would you get the density functions? So let's look at one more of these for Weibull shape parameter k equals 1. That's the exponential distribution exactly. Let's do the same thing. Well, it has the same, I wonder what these look like. Well, they're going to move to the right, and indeed it does for correlation coefficient 0.9. There it is for 0.5. Interestingly enough, look at this density now, though. It doesn't look like an exponential distribution at all. The maximum of two correlated exponentials actually moves out and begins to look more like a log normal distribution or kind of a Weibull distribution that you started with, although it's not an exact Weibull. What if you go to 0? These are independent now. That actually does have a closed form, the maximum of two Weibulls, which is basically the product of the CDFs. But the correlated cases, so far as I know, don't have have no closed form, and so there's the minus 0.5, minus 0.9, minus 0.99. So now we have it. Let's put it to work in terms of chance of whatever information to aid decision making. Let's just consider, and Phil came up with this example, and very helpful in that regard. Thank you, Phil. Let's consider two identical aging aircraft for which parts are no longer available. Their manufacturers have gone out of existence, and so really the life of the program depends on how long these aging aircraft last, and once they fail, they fail, at least in this simple example I'm using. Let's just say the projected life of the program is 12,000 sorties. You could put in flight hours if you wanted. For this example, I just used sorties. That's the projected life of the program. And let's just say that older things are more likely to fail by a small amount, so I'm using this k equals 1.5. And in this case, the lambda, I put 10k here. I meant to say, that's right. And let's just say you've modeled it with a Weibull distribution where the lambda, the scale parameter, is 10k. And you ask the question, what's the chance they'll both be out of service before the end of the projected program life, 12k sorties? Well, that is simply answered now because I can just plot these cumulative distributions that we've just calculated. And it turns out that, for example, if they are 100% correlated, well, then if one fails, they'll both fail. And the probability that they'll both be out of service before 12k, which is here, the end of the program life, that's about 73%. If they are independent, then rho equals 0. If one fails, the other one might not have failed, so there's a smaller probability of both being out of service for the end of the program life, and that turns out to be 54%. And if they're correlated, it's somewhere in between 60 and 67%. So that's just an illustration. I mean, there are lots of other chance of whatever questions one could ask, but it's just an illustration of how you can use this quantile table once you have calculated it, and you store the quantile table, and then you can, in closed form, quickly answer any such questions that you might have. So let's do one other chance of whatever question. The question that I stated at the beginning: how much does assuming independence overstate the reliability of a redundant component with a common failure mode? Presumably, a lot of people have modeled this and assumed independence of system components that may well have a common failure mode, and then made investments based on that, and they would be actually overstating by assuming independence the actual reliability of the system. And in fact, what you can easily calculate from this table that I've just shown here, here I've normalized for the median of the sum of two Weibulls. I've normalized that to 1, and then the question is, if those two Weibulls were actually correlated with a 50% correlation or a 90% correlation, how much would you be overstating the median by assuming that those were in fact independent when they weren't? And the answer is, if the two systems are 90% correlated, the two components are 90% correlated, the median would be only 62% of the case where they were independent, and so forth. And that's different for different shape parameters, not surprisingly. But anyway, there are a multitude of such analyses that could be done once you have the closed form information and the metalog representation. I'll do one more of these just for completeness. What if a system fails if either of two components fail, and both those components are modeled as Weibull, and the same thing on the correlation coefficients? And yes, now we can calculate a quantile table, and again, that's based on 500 case simulations, as the minimum of two identically distributed Weibull variables with different shape parameters, different correlation coefficients, and for the same, I'll use the same probability vector, and I still just use my computer to do 500 case simulations. And by the way, these numbers hardly change at all if you use a different random number seed. But if you wanted more detail here, you could obviously go 5 million instead of 500,000, and if you wanted more detail, you could simulate for 1.25, you could simulate for lots of intermediate values, you could expand the table. I'm just making this a simple illustration, but if you had one of these you were going to do and use again and again and again, you'd probably want to simulate a larger table than the one I'm showing here, just so all the interpolations would be even all that much more accurate.